The last part of this chapter, we're going to look at phase equilibrium. Equilibrium means that we have a balance between going from one phase to another and back. Doesn't mean we have the same number of particles in the liquid as we have in the solid, or the same number of particles we have in the gas as we do in the liquid. It means that the conversion from liquid to gas is happening at the same rate as the conversion from gas to liquid. We can only have an equilibrium in a closed system. And when we have, for instance, between a liquid and gas, the rate of evaporation and the rate of condensation happening at the same rate, then we have a phase equilibrium. The pressure that a gas exerts above a liquid in a container is called the vapor pressure. If I have a very high vapor pressure, that means that a lot of liquid has gone to the gas phase. I have something that is called a volatile substance. Volatile means easy to evaporate. And volatile substances are due to weak intermolecular forces. So these are going to be substances that have London dispersion forces, primarily nonpolar substances, primarily organic nonpolar compounds. You can also have vapor pressure again of solids and liquids. Solid going to gas, that process is called sublimation. Going the other way from a gas to a solid is called deposition. So the equilibrium can only occur when we have a closed container. If we have an open container, like an open glass, an open beaker, solid just sitting in the room, we're not going to have that. We're going to have something continually going to the gas phase based on temperature. We've seen heating and cooling curves. We saw them before in thermodynamics. We're going to take a look at them again a little bit more quickly. Temperature on the vertical axis, time on the horizontal axis. The diagonal line represents single phase. So the single phase here would be solid. Single phase here would be liquid. Single phase here would be gas. Where my line is horizontal, I have a constant temperature. I have a phase change. So I have solid going to liquid, or melting. When my line is horizontal here, I have a phase change from liquid going to gas. So I have boiling. We can calculate the energy for any of these phases. Again, from Chapter 6 on thermodynamics, we can figure out the total amount of energy needed to go from a solid to a gas. Again, if we know the specific heats, if we know the heats of vaporization and heats of fusion, we can find the energy involved. What we're going to do, though, now really is compare our heating and cooling curve to a phase diagram. A phase diagram relates temperature and pressure of a substance to what phase it exists in. So here we have three phase diagrams. The first phase diagram is that of water. Pressure for phase diagrams is the vertical axis, temperature is the horizontal axis. So we see the solid phase, generally low temperature, high pressure. We see the gas phase, generally low pressure, high temperature. And then the phase in between, where both are relatively high, is the liquid temperature. So each of these curves is an equilibrium line. So this line right here is the solid gas equilibrium. That is where the solid is subliming at a given temperature or pressure, and it's at equilibrium doing that. This line is a straight line, at least for water, and this is the solid liquid equilibrium. This line is the solid liquid equilibrium, so that would be melting. So as the pressure increases, the temperature at which I need something to melt decreases. It's a solid line, and we'll talk about the way it's angled momentarily. This line is the solid gas equilibrium. That would be boiling. As the temperature increases, the amount of pressure I need to get something to boil increases. Conversely, if the pressure drops, the boiling temperature will decrease, which is why water will boil at different temperatures depending on the altitude you are. If you remember that the definition of boiling point, normal boiling point, is when the vapor pressure equals atmospheric pressure. If I have really high atmospheric pressure, say at sea level, boiling temperature is going to be 100 degrees Celsius. If I go up to Denver or to the top of Pikes Peak, atmospheric pressure is way lower. So because the pressure is lower, the temperature at which something will boil is significantly lower as well. And that's what a phase diagram will show us. A couple other pieces of information on a phase diagram. The triple point. Triple point is when all three phases are in equilibrium. Solid, liquid, and gas all coexist all are going from one phase to another at the same time at the triple point pressure and temperature. The other important point is the critical point. And the critical point is the temperature above which no pressure will make the gas condense. The kinetic energy of the gas is just too high, and no amount of pressure is going to make those particles get close enough so that their attractive forces can hold the particles together for any significant length of time to make it become a liquid. So critical point, triple point, phase diagram is different for every single substance. So we have water on the left, we have carbon dioxide on the right, and the main difference, other than the pressures and the temperatures at which these values occur, is the angle of the liquid-solid equilibrium line. If you look at water's equilibrium line for solid-liquid, it has a negative slope. Most phase diagrams are like carbon dioxide, and the solid-liquid equilibrium line has a positive slope. If the slope is positive, what that tells me is the solid is generally more dense than the liquid. If I have a negative slope, as I do in water, that tells me the solid is less dense than the liquid. We know that ice floats, so solid H2O is definitely less dense than liquid H2O. And one of the ways we can see this is in the water phase diagram. We have a negative slope for the solid-liquid equilibrium. The last phase diagram we're going to look at way over on the right is that of carbon. And there are some substances that have multiple phases. So if we look at the carbon phase diagram, there are two solid phases. The graphite and diamond are both solid forms of carbon. We talked about what the diamond crystal lattice looks like compared to the graphite crystal lattice. In order to get from one to the other, temperature range is about the same for both solids, but you need to really crank up the pressure. If you want to make a diamond, you need huge amounts of pressure. Notice that 10 to the 9th through 10 to the 11th kilopascals. Temperature is not anything to sneeze at either. It's pretty high, up to 4,000 Kelvin. Freezing is 273, remember. So we're way down on the low end here. So that's how diamond was made in the earth, is under huge pressure, under very high temperature near the liquid layer of the earth. Industrial diamonds are made by taking graphite and heating it under very high pressures. And so synthetic diamonds are now made routinely to use on saw blades and engraving pens and things like that. You can have liquid carbon and vapor carbon, but very high temperatures and pretty high pressures as well. Not very common occurrence. So this takes us through chapter 10 and our look at solids and liquids. And our next chapter will go and combine these and create solutions. This finishes our look at solids and liquids for chapter 10.